So double integrals in a non-rectangular region were quite simple to do, yeah, and we did a couple of examples. But what about triple integrals? So triple integrals in non-rectangular regions. How do we do this monster? Don't worry, it's actually very easy, okay? So let's say that this strange volume here, and this volume here is placed between an upper surface, which is this surface, E2 as a function of x and y. It's also above this lower surface, which is a surface E1 as a function of x and y. And it is also contained within this area in the xy plane, okay? And this area in the xy plane is limited between cx as the minimum value of y and d of x as the maximum value of y, okay? And also it's limited between x equals a and x equals b. So we want to integrate over this volume. So we want to do the integral of some arbitrary function over this volume, okay? So how do we do it? First, we need to choose an order of integration. So let me choose the following order. We first integrate along z, we then integrate along y, and we then integrate along x, okay? So if you do this, you start from the beginning, so z. So draw a line from an arbitrary point in the xy plane in the z direction, okay? So this is a line that starts from an arbitrary point and grows in the z direction. Okay. And now you ask yourself, when does this line enter the integration region and when does the line exit the integration region? Okay, so obviously it enters the integration region here in this surface E1 of xy, and therefore that is the lower limit of the inner integral, which is with respect to z. Okay, so that's the lower limit of the z integral. And it exits this integration region on this surface here. And this first surface here is the surface E2, which is a function of xy. So that will be the upper limit for z. Okay? So that will be the inner integral. So this inner integral will be a function of x and y only. We have gotten rid of z, thanks to integrating through z. So this means that this function of g of xy, we now need to project the volume V. So all this volume, we now need to project it into the xy plane, because now we are left with a function of x and y. Yeah. So this is the projection. Okay. So this projection is now a region in two-dimensional space. So now we could choose to integrate first along y and then along x, or first along x and then along y. But in this case, it's easier to integrate first along y. And that's what I wrote here. So after z, we integrate along y. So now what do we do? Now you picture you are in the xy plane, which are the two variables that are left. You draw a line in the direction of y, which is the variable over which we are integrating next. Yeah, this is our next variable of integration. And we think about when do we enter this region and when do we exit this region. So we enter this region on this line, y equals c of x. So we could write it as y equals c of x. So that will be the lower limit for the integral of y. And we exit this region on y equals d of x, which is this function here, which is the upper limit of the integral for y. Okay? So this is great, because now we are integrating a function of x and y with respect to y, and the limits are a function of x. So we are left with only a function of x, h of x here. Okay? So this function of x has to be integrated where? Well, we have to project this area into the remaining axis, which is the x-axis. So we project it into this axis. So when you project this area into the axis, you are left with a line segment that goes between a and b. And those will be the limits for the x integration. Okay? So notice, as always, very important, the limits for the inner integral must not include z, but they can include x and y. But it's fine that they include x and y, because later we are going to integrate with respect to y and with respect to x. So we will get rid of those x and those y's later. So it's fine to have x and y in the limit. Next, the limits for the y integral They cannot contain sets because we already got rid of all the sets here. We don't want to know anything about sets anymore. But also we want to get rid of y because we're doing the integral through y. And this means that these limits can only be a function of x, which corresponds to these two functions. And then finally the outer limits, which is the last variable of integration x, they must be constants always. Because otherwise, if we had x, y, or z in the limits, our final answer would depend on x, y, or z, and it cannot be the case, right? When you integrate over x, y, and z, you get rid of x, y, and z. So the outer limits are always constant. Okay? So I hope that was more or less clear, and I think it can be very easily clarified doing an example.